Welcome to the Chemistry Cauldron section on reviewing essential content from the Year 10 course that you need to have really nailed so you can understand and achieve to your best through prelim chemistry. One of the areas which I need to review at this point in time is ionic compounds. There are also covalent compounds, which you need to look at the covalent compounds review episode. Today we're going to be looking at ionic compounds. Now remember that ionic compounds are formed when you have a metal joining with a non-metal atom. You can see here at the periodic table beside me that we can group elements based on whether they're metallic, whether they're semi-metals, or whether they're non-metallic. And when you have a metal plus a non-metal, that's when we form an ionic compound. We've also got to remember that when ionic compounds form, they do not form discrete molecules that float around, like covalent compounds or what are called molecular compounds. Ionic compounds are actually made up of large arrays of positive and minus ions together in a lattice. You can see here that with sodium chloride that the positive and minus ions are alternating within the lattice and held together in a crystalline structure. That gives rise to a variety of properties which we'll examine later. But just keep that in the back of your mind there, that when we form ionic compounds, they're large crystalline structures. The positive and minus ions are actually held together by electrostatic forces. Now, when we form ionic compounds, we've got to remember that the neutral atoms are actually forming ions. So how do they do that, and how can we show that in chemistry with an equation, what's called a half equation? Let's have a look at that. Starting off with metal ions tend to lose electrons to satisfy their outer shell, so that we have an octet. You may remember from Year 10, or if you look at that Chemistry Cauldron episode on atomic structure in valency, it was said there that atoms are more stable when they have a full outer shell. Other than helium, most atoms have 8 electrons in their outer shell, and you get rise to this concept called an octet. And they want to get the same electron configuration as the nearest noble gas. So if with a metal, let's just call it M, any metal for the moment, it wants to lose the electron in its outer shell and attain the electron configuration of the nearest noble gas. When it does that, it forms a positive ion and it loses that electron. So we put the electron on the right hand side here. So that the positive and the minus, if you add them together, should be the same charge that's on the left hand side, which is neutral in this instance. So let's take an example. Let's take sodium. Now if you remember, if we wanted to draw the full electron configuration of sodium, we would have to draw each particular electron in the shell. So let's start in the middle. We start off with the nucleus. In the first shell we have 2 electrons. In the second shell we have 8 electrons. So let's draw them in. And then in the outer shell we have 1 electron. So that's sodium. Okay, now the nearest noble gas to sodium is neon, and so it wants to lose that electron in the outer shell and attain an octet of 8 electrons in its outer shell. So that electron is given up. Now remember that electrons don't just float around, they have to go to somewhere. Okay, so let's find out how we write that. So sodium now has a 1+ charge because it has more protons in the nucleus than it does actually electrons surrounding it. So it has a valency of +1. Right? If I was to draw that structure again, it would look something like this. Okay, there you can see that it's there. And if you look very carefully, you can notice that the electron has been removed and we have 8 electrons in the outer shell. It is now full and satisfied. And so now, of course, we have to write in that we have this electron being lost to the outside there. And so we have formed a positive ion here. So metals lose electrons to form positive ions, and we call them cations. Okay, there's my cat. So if you remember that a cat has large positive eyes and it's a shape like a cat, and cation might be a particular way that might use to remember the charge plus the name on the ion. So that's forming positive ions. Let's now have a look at forming negative ions. Alright, as you can see here that we've got a non-metal, and the non-metal gets an electron to form a minus ion, which we call anions. So let's just draw the electron configuration of an example here. Let's say chlorine, and see how that works in terms of where the electron goes to give it a stable outer shell of 8. Okay, as you can see now, we've got the chlorine atom over here, which is neutral. It's got 7 valence electrons in its outer shell. Okay, it's in group 17, or sometimes you might learn it as in group 7. So it's got 7 around the outside. It wants to get an electron to maintain a full outer shell. So therefore, here's the electron. When it gets the electron, it now has a full outer shell, and therefore it has more electrons than protons, and consequently it has a minus charge of 1, which is we call an anion. We can do shorthand for this. We can write down that we have 2 electrons in the first shell, we have 8 in the second shell, and then we have 8 in the third shell. So we can write the electron configuration as a series of numbers, 2, 8, 8, instead of actually drawing all of them in, which takes a long time. Hence, that's why I've edited them out. Okay, so now we look at how we form ions, both cations for metals and anions for non-metals. And so now we're going to look at some other examples to see how that goes in terms of naming and writing formula. Okay? Okay, here we now have a variety of situations which we're going to look at, and how we write formula for ionic compounds, and also how we do some naming. You can see on the right hand side here I've just written down some polyatomic ions, poly meaning many, atomic meaning atoms. So therefore they're actually ions that are made up of more than one atom. And so I've got the anions up the top there, some common ones, and I've got a cation down the bottom. So of course you should memorize these. We've got a hydroxide, we've got a nitrate, we've got a carbonate, sulfate, and a phosphate, and then I've got the ammonium cation down the bottom as there. Now, when you first get atoms, you've got to work out what their valency is, their charge, and that's pretty simple when it comes from elements coming from groups 1, 2, 3, 4, etc. Because generally, the charge on the atom is equal to their group number. It's equal to the number of electrons in the outer shell. So all group 1 cations have 1 electron in the outer shell, and group 1 is metals. They lose that electron, so therefore all group 1 has a positive 1 charge. Group 2 consequently also has 2 electrons in the outside shell, therefore it loses those 2 electrons, giving it a 2+ valency, and so on. Some elements, however, do tend to have variable valencies, and some you just need to remember. So for example, when we get down here, we're going to see that silver is a transition element, and it has a 1+ valency. Generally, transition elements have a 2+ valency unless you're told otherwise, because there are some elements that do have variable valencies, and we will discover those as we go through the course. So let's start off with these and start writing their formula and naming them, and we'll talk about the rules that you need to learn to name them. Okay, so we're starting off here with strontium. Strontium is in group 2, so therefore it has a 2+ charge, or 2+ valency. Chlorine is in group 7, and therefore it has 7 electrons in the outer shell, and therefore it needs 1 to attain the octet, and so therefore it would have a valency of -1 when it has a full outer shell. So when we look at these two here, we can do it, there's 2 different methods. There's the crisscross method, and then there's the method, just if you're very good with maths, you can look at that and work it out in terms of balancing charges. Let's do the crisscross method. The 2 goes down to the bottom of the chlorine, and we've got a -1 here, so that 1 goes to the bottom of the metal. In this case, we're looking at strontium. So it will be SrCl2. That's the formula. Okay. When we go to name it, we say the name of the metal first. So here we go, strontium. Then we put the name of the non-metal second. However, we change the ending of the name from "ene" to "ide." And so instead of it being chlorine, it would be chloride. This second example here, as I said a moment ago, that silver's +1. Iodine is a halogen, it's in group 7, and so therefore it's got a valency of -1. Here, if we do the crisscross method, you can see that we just have 1 being a subscript for both of them. When there's 1 atom there, we don't need to write in the 1, because if there wasn't 1 there, it wouldn't be there, like if it was a 0. But if there was 2 there, of course, we would write a 2 in there. So we don't need to write a 1 there. It's a little bit like maths. When you have x, you don't write 1x. But if you have lots of x, you can write 2x. Okay, so if we write the formula here, we have the metal first, then the non-metal. And so that's silver. And then we write the name of the metal first. And then we have the non-metal second. In this case, it's iodine. So instead of it being "ene", we change it to "ide". So it's iodide. Here we have iron and sulfur. Now, iron is one of those elements that can have a variable valency. In this case, let's just make it a 3+ valency. Sulfur is in the same group as oxygen, and in that group there, they've got 6 valence electrons, and so therefore they need 2 to get a full outer shell of 8. So hence it would have a valency of 2-. Now if we do the crisscross, the 2 comes in front of the iron, or I should say behind the iron, in other words a subscript, and the 3 goes down below the sulfur. And so there's the formula there. Now, because iron can have a variable valency, we can't just go, oh, that is iron sulfide. Because if we had that being 2+, right, we could have another formula. We could have Fe, and that 2, if that was a 2+ there, they would then go over to give you Fe2S2. But we like to have the lowest common denominator here, so that would be 1. In a ratio of 1 to 1. So the formula would be FeS. Now, if you were just to call that iron sulfide, well then that would be iron sulfide. They're 2 different compounds, so we need a way to distinguish between them. So if you remember from year 10, we actually have Roman numerals to delineate the types of valencies that the metal have. So in this instance, we've got a 3+ valency, and so therefore we would say it's iron 3 sulfide. Okay, now we're getting to a case now where we have a polyatomic ion here. So you have to remember that nitrate has a -1 charge. Lead can have multiple valencies. However, we've got to remember here that generally it's a 2+. So let's put a 2+ here. Now, because this goes around as one particular unit, when we put the number on the outside, we have to put brackets around the nitrate to say that we need 2 lots of the nitrate to balance off the charge. And so sometimes people, when they do the crisscross method, get a bit confused here. Where do they put it? But if you think of the mathematical balancing charges method, it makes sense, because you say to yourself, okay, we've got 2 positives. If each nitrate unit has a -1 charge, then we're going to need 2 complete nitrate units to balance that charge. And so for every 1 lead atom, we have 2 nitrate polyatomic ions. So it's Pb, NO3, but then a 2 on the outside, because we need 2 nitrates for every 1 lead to balance the charges. To name it, we just name the metal and then name the polyatomic ion. So that would be lead nitrate. The last one here is we've got a polyatomic ion again. It's a phosphate, so we have to remember that it's a 3- here. Magnesium is in group 2, so therefore it's going to have a valency of 2+. And so now we then have to do is do the crisscross method and go, okay, the 3 goes down to the bottom of the magnesium. We put a bracket, and the 2 goes there. Okay, so the ratio is 3 magnesiums for every 2 phosphate. And so we would call that magnesium phosphate. Alright, so that's pretty straightforward, and there's more practice questions in the textbook, of course, and I'll try and also put a file below this in the description as well for you guys to practice with answers. Try to do them without looking at the answers first. There's one last more thing we have to do before we go, and that's actually working out what the valency is of a compound if you don't know what the compound is. I'll show you what I mean. Okay, this is the last thing we're going to be talking about in this particular episode, and this is when you get a question where you don't know what the metal is, but you know what the non-metal is. So here we've got X2S, and the question usually says, what is the valency of X, or what is the identity of X? So here it's relying on your understanding to know that sulfur forms a 2- valency. So if sulfur is a 2- valency, what is X going to be? Well, you could do this just by inspection, by looking at it, or you could do it mathematically. If you just look at it, and remember the crisscross method, then the 2 comes from the top of the sulfur, and there's a 1 there, which comes from the top of the X. So therefore, you can say that X is positive 1. Mathematically, you could say, okay, we have 2 X's in the compound, so let's just put X as an unknown, and we know that sulfur has a charge of 2-, and overall the compound is a neutral compound, so we put 0 there, and then we solve for X. So we go 2x minus 2 equals 0, 2x equals positive 2, x is equal to 2 divided by 2, which is positive 1. Right? So there's 2 ways we can do that, whichever one you feel most comfortable with. This method here works very well when you start getting to larger, more complicated compounds. Okay? Simple ones by inspection will work. Let's do the second one. Okay, so here we can know that we've got a sulfate here. We know that sulfate is 2-. There we can see the 2 there from the sulfate. So therefore, Z must be 3+. Okay? Alright, so I hope that improves your understanding of ionic compounds. We will look at them in more detail later in terms of their structure and their bonding and their properties. But that's a quick revision of Year 10 essential content. Alright, well, keep looking at the other ones, keep doing your homework, and I'm sure that if you revise frequently, there's no reason why you can't get a band 6. Alright, that's it. See you next lesson.